number 3, let vector v equal the component form 3, 4, and suppose vector w is vector pq, meaning it starts at P, initial point P, terminal point Q, using these points. So the first thing we need to do on this problem is what we did on example 1. We need to find the component form for vector W. To do that, we're going to take the terminal point x and subtract the initial point for x. So subtracting a -3 means we will actually add 3. And then we'll take the terminal point for y and subtract the initial point for y. So that will give us +1, -2 for vector W. Let me just check my notes and make sure I'm doing that right. Yes. Okay, so now if we want to add vector V and vector W together, we just take the x values. So the x value for vector V is 3. The x value for vector W is 1. We're just going to add those together. So 3 plus 1. And then we're going to add 4 plus -2. So 4 plus -2, 4 minus 2 will be 2. So that gives us a resultant vector of 4, 2. Okay, we're going to draw a sketch to represent this sum geometrically. So let me just... Now, if you try to actually follow the coordinates that they gave us for P and Q, we would want to have an XY axis, and we would go left and up for P, and left and up for Q, and it would be a vector up here somewhere. Now that we've found the component form, we don't care about P and Q. It doesn't matter where it starts and ends. It just matters that it goes right 1 and down 2. So we're just going to start with vector V first. So let me get my vector here. Vector V, I'm just going to start down in this corner somewhere because vector V is positive, positive. So just start here somewhere. So I want to go right 3, sorry, and up 4. There's my vector V. And then for vector W, I start at the end of vector V, and I'm going to go right 1 and down 2. So there's vector W. That leaves us with the answer to our addition, which we call the resultant vector. I accidentally touched the screen. So the resultant vector would be right there. I think I can move that a little bit to make it a little more accurate, maybe. Will it let me? Yes. Awesome. Okay, so just to label this in our picture correctly, this would be V, this would be W, and this is V plus W. So graphically, that's what adding vectors together looks like. Okay, vector addition adheres to properties of addition, like the commutative property. You can add them in different orders. So in other words, we could have been able to draw vector W first, and then vector V, and the length of and direction of our vector V plus W still should have turned out to be 4, 2, even if our picture might look slightly different. The associative property, if you have more than 2 vectors that you're adding, it doesn't matter what order you add them in. The identity property is if we add 0 to a vector, we still end up with the same vector. And the inverse property is if we add a negative vector to our vector, we get 0. So the inverse of vector V is -V. They have the same magnitude, but they go opposite directions. To subtract 2 vectors, we simply add the inverse of the vector we are subtracting. Do you want me to show you what that would look like on a picture? I'm trying to remember what the next example is if we actually get a chance to show you that. Probably not so much. So just for fun, if we wanted to do V minus W instead of V plus W using the ones we just did, then vector V would go right 3 up 4. I should have used my line drawer tool because that was bad. Okay, so let's say that that's right 3 up 4. But then instead of W being right 1 down 2, it would be left 1 up 2. So it would go the opposite direction, kind of like we do when we're graphing polar coordinates, right? So a negative just means it's going the opposite direction. I want to change this to a different color just because I've been using red for the resultant, not that it really matters. Okay, so then if the resultant of subtraction for these would actually be longer. So that would be v minus w, which is actually longer than v plus w, and in an entirely different direction. Okay, I'm going